Bismillahirrahmanirrahim. Assalamu alaikum, and welcome to Lecture 3 of the Celestial Lessons. The 17th day of the Ramadan is behind us. The full moon, it has been full moon, and now the full moon is, and now we are entering the gibbous waning phase of the lunar cycle. The moon is losing light from right to left. One of our viewers sent me a photo of the full moon today. This is Atif Khan, who Thursday night took a photo of the full moon. An impressive, detailed photo with his camera. I would first like to elaborate on lectures 1 and 2, beginning conveniently with the lunar phases. Quite topical. We note that the sun always illuminates half the moon. Yet the half that we see does not coincide with the illuminated half, the half that the sun illuminates. We see a section, and hence the phases, the different phases. Except at the full moon, when the half that the sun illuminates and the half that we see is the same half. I would like to elaborate on the lunar and solar eclipses. We recall that the moon's orbit around the Earth is in a circle, and this circle is in a plane that is slanted with respect to the plane of Earth's orbit around the sun. So due to this slanted plane, the moon is higher or lower than the sun. Except at the places where the two planes intersect. These are the places of the lunar, these are the lunar nodes. And since here the moon is not higher or lower than the sun, eclipses can happen. A lunar eclipse, if it is full moon, and a solar eclipse, if it is new moon, and the moon happens to be on one of the lunar nodes. There is a curious fact about the solar eclipses. The moon's angular size and the sun's angular size happen to coincide, allowing an overlap. Had the moon been smaller on the sky, a complete overlap would not have been possible, and a total solar eclipse would not have been possible. The sun is 400 times greater in radius than the moon. But it so happens that the distance from the Earth to the sun is also about 400 times greater than the distance from the Earth to the moon. These two cancel each other, and the angular size of the moon and the angular size of the sun coincide. There is no known explanation of that coincidence. There is another curious fact about the moon, and it is to do with its rotation. When the moon orbits, we should really see a different side of the moon on the other side of the orbit. But the moon always shows the same side to us. What is happening is that the moon rotates about itself while it is orbiting. And the rotation about itself and the orbit around the Earth is synchronized in such a way that it always shows the same side to us. So we had to await satellites to see the other side of the moon. However, in this case, there is an explanation. The Earth's gravity pulls differently on different parts of the imperfectly spherical moon, and so it applies an aligning turn that prefers the moon to always show the same side. Last time I also talked about the meteor showers. I mentioned a meteor shower happening these days in Aquarius. Meteor showers are the technical term, or meteors are the technical term for shooting stars. These are particles called meteoroids that are trails from comets or asteroids. This is a phenomenon that is happening in our atmosphere. The meteoroids enter the atmosphere, burn and glow. Some meteors are sporadic. They can happen at any time. However, meteor showers are due to the Earth's encounter with trails with meteoroids on its orbit. And this encounter is annual, happens every year at around the same time. There is a time window, and this window has a maximum, a time of peak activity and a large number of meteors. The meteor showers are named after the radiant. The radiant is the place from which they tend to appear on the sky. And so I've listed 5 active meteors that you may want to note. I have experience with the Perseids that have their maximum on the 12th of August with a very high rate of about 100 meteors per hour under ideal conditions. So these are named after the places on the sky that they appear, and let us now find those places. So let us locate the radiance. Now, when looking for the meteor showers, or when looking at the sky, one need not look at the radiant itself, but can look. The meteors may happen a distance away. In the case of the quadrantids, happening on the 4th of January with a high rate of 120 meteors per hour, the quadrantids refer to an old constellation, or the name that is no longer in use today, but it is in the constellation Boötes. The Boötes is the kite-shaped constellation where Arcturus is. Recall that we used Arcturus in order to find Virgo before. Boötes is near the plough that we are by now familiar with. So the radiant is in Boötes of the quadrantids. The Eta Aquariids, Eta a Greek letter, presumably because there are other meteor showers also happening in Aquarius. This one is around this time, the 5th of May, peaking around this time, or has peaked but is still active, with 55 meteors per hour. It's in Aquarius, which is part of the zodiac. And one can see that the software has singled it out here. Now, Aquarius is a bit irregular, might be difficult to find, so one may locate it using our favorite Cassiopeia, our favorite constellation, and the W, and use one of the legs of the W to find the constellation Pegasus, which has a square, and then Aquarius is near its square. And there are the Perseids. The Perseids can also is in the constellation Perseus, and it can also be found using Cassiopeia, using the other leg and going down. And here is the constellation Perseus. So the radiant is here. That's the 12th of August, and with a high rate of about 100 meteors per hour. So the prospects, if the sky is clear, the prospects are good for having seen at least one. Then there are the Orionids. Recall that Orion is a winter constellation, and so this is happening in October, the 21st of October, peak with 25 meteors per hour. And I need not introduce Orion. The Geminids in the constellation Gemini above Orion, the 13th of December, with a very high rate of more than 100 meteors per hour. So these are the meteor showers. The one we talked about, the Aquarids, at the end of lecture 2 last time. A viewer suggested a piece of software and app for the phone called SkyPortal. I hadn't used it before, but I found that it's a wonderful app that I can recommend everyone to download. It is free, and it's developed by Celestron, a manufacturer of telescopes. SkyPortal has a compass mode. So pressing the compass, one can point the phone to a part of the sky, and then one can see the stars in that direction. It also has the possibility of rewinding and fast forwarding the sky. It may be the night sky or the one during the day, the sky in general. Here it's during the day because the sun is here. It was at 3:45 p.m. More importantly, it has a night mode where everything is red. And this is because red light does not desensitize the eyes. Normally, the white light from the phone would desensitize the eyes and would overpower the light from the stars, and the eyes would no longer be sensitive to the stars. But with red light, this doesn't happen, and so it's quite convenient to have with you outside. It's much more convenient than star charts or these star wheels, where one needs a light in order to read them. But here one has red light emanating from the screen, so quite convenient. You may have noticed that some objects are brighter than others on the sky. Some stars are brighter than others. This may be intrinsic, or it may be due to the distance, because stars that are more distant appear dimmer. The brightness is described by what is called the apparent magnitude, M. The brighter an object is, the smaller M is, so it works in the opposite direction. And M of about 6 is the limit of visibility for unaided eyes without the help of telescopes or binoculars. Now, this scale is not a linear scale, so an increase in 1 of M means that the object is about 2.5 times dimmer. An example, Sirius has a magnitude of about minus 1.6, so well below the limit of 6. It's the brightest star on the sky. SkyPortal can also do magnitude filtering. Here we see what happens when we do not allow stars that have a magnitude larger than or are dimmer than 0. So we can really only see Venus and the Sun. I should not say stars, I should say an object on the sky, because Venus is a planet. We can increase this limit to 5, which is near the limit of visibility, and we see more stars appearing. And as a foretaste of the unseen, with a telescope, one really sees that there are many, many more stars in the sky that we just don't have access to, which can be accessed with binoculars as a first, and then with a telescope. So many stars, an immense number, that are in the sky that we just don't notice, but they're there. Let us look at the other planets, the non-classical planets, Uranus, Neptune, and Pluto. Uranus is barely visible with a magnitude of about 5.9, so it's just the limit of visibility. Neptune has a magnitude of 7.9, so it is invisible to unaided eyes. One needs a telescope in order to see it. And Pluto is completely out of reach with a magnitude of 14.3. And no wonder that it was only discovered recently, or about 100 years ago, which is not very long ago. Then there are the asteroids. One can also observe those, but again, a magnitude of 8.4 is dim, too dim for unaided eyes. SkyPortal has more functions. One can click on the objects on the sky and get a description of the object. There is a list of meteor showers as well. Some meteor showers that I did not mention that are weaker. Leonids, for instance. And here one sees that there are other meteor showers in Aquarius, Delta Aquarids and Eta, the ones that I did mention. Then there are more advanced ones. These are for those who have telescopes or binoculars. One can see a list of comets, and comets are orbiting icy, dusty, gaseous visitors with a tail. Derived from the Greek kometos, which means wearing long hair due to their tail. And in their name, they might have the letter P, so 210 P Christensen, for instance. This is a comet that's quite dim, but the P means it's periodic, so it's known to return. So they are orbiting the sun in very eccentric orbits, very elliptical ones. Also, SkyPortal has suggested objects to look at, but many of them are too dim for just stargazing without telescopes. So here one has the Andromeda galaxy, which can be seen should be visible with, yes, it is a less than 5, so that means it should be visible with, if one looks very carefully. I have not looked for it and haven't been able to see it so convincingly. Lecture 3. Now we get to the main body of the lecture, is called the hesitation of light. And here we are reflecting on light, the light in the sky, in the atmosphere, and on Earth. We recount the discovery that light travels at a finite speed, and the unexpected realization that light is electromagnetic. So the arrival of light is not immediate. However, it does appear to us to arrive instantly when we turn on a lamp. In fact, it has a large but finite speed. This was first demonstrated by the Danish physicist Ole Rømer In order to notice this large speed, or large but finite speed of light, we need large distances or precise instruments to notice it. So we turn to the sky for the large distances and observe Jupiter from Earth. Now Jupiter has moons orbiting Jupiter, and sometimes they're hidden behind Jupiter, so we can't see them because we only see reflected light reflected from the sun, the sun being the only source of light. So we consider the emergence of one moon from the shadow of Jupiter, because we cannot see the moon when it is screened. After the exit from the shadow of Jupiter, light from the sun shines on the moon and we can see it. So let us suppose that light has a finite speed. What would then happen? What difference would we see in our observations? We consider observing from two different positions, L and K. The predicted reappearance of the moon would be delayed when looking from the more distant position, K. This is because it's delayed by the time it takes light to travel the extra distance. This is a matter of minutes. You may have heard that it takes the light 8 minutes to come from the sun and reach Earth. So this is also a matter of minutes. And we can estimate this speed by taking the extra distance and dividing it by the delay we find in the reappearance of the moon, of one of Jupiter's moons. And this Römer did, and he did it successfully. However, he did not get a very precise value for the speed of light. But he did establish that it had a speed which was very important, and whose importance we can now fully appreciate. The modern value of the speed of light is about 300,000 kilometers per second, which is also 186,000 miles per second. Now back on Earth, we can look at other aspects of light, how it behaves. There is the property of reflection that some surfaces have. Some surfaces reflect light. The light is really rejected by the surface. And when light is reflected, the incoming angle equals the outgoing angle with respect to the surface perpendicular. So we are really fooled. There is an image created in the mirror, even though the object is elsewhere. What happens is that we place the object or the image in the direction the light was last seen coming from. So we place it here. There is also the phenomenon of refraction. This is the sudden deflection of a ray of light between two different mediums. Here it could be vacuum, air, or it could be air and water. So with refraction, an incident ray, a ray coming in, gets deflected, gets a different angle at that interface. And this is because the light speed is different in the two mediums. Effectively, it is lower in a medium different from the vacuum due to interactions of light with the medium. The angle depends on the incoming angle, this one, and the properties of the two mediums. Between air and water, this is perhaps a familiar case. we will think that a fish is where it is not, because if the fish is here, then the light goes up and gets refracted, deflected, and then if we were observing from here, we would think that the fish is over here, but it was really here. One also sees the sudden change when one puts a straw in a glass of water. There is another effect of refraction which is perhaps less familiar, and that is the concept or the phenomenon of the mirage. And the two different mediums that I was talking about before are here hot and cold air. So one medium being cold air and the other one being hot air. And this is known to happen in the desert. The air near the surface in the desert is hot, it's warmed by the sand, while the air above is colder. The refraction is less sudden. There is also a gradual change in the temperature, but it can still be significant. And so what one sees is, if one looks at a palm tree, one would be able to see it because light is coming from the leaf or the whole tree or the building next to it. But one may also see another image, and this is the image where a part that we were not supposed to see, that would normally, without these two different mediums, that would normally just go down, it gets deflected by the hot air, and so reaches our eyes, and we attribute it to have come from a certain direction, and that is inside or into the sand. And so we see a mirror image, the mirage. Another surprising fact that I only learned last year, the setting sun is also an example. The setting sun that touches the horizon is actually below it. So once we see the setting sun touch the horizon, it is below it. If one was to fly to the sun, then one should really be aiming in a different direction. And the reason is that the light from the sun goes from vacuum in outer space to air. And so what happens is it gets deflected at the interface between vacuum and air. So it gets directed to give us another position. Another effect of refraction, which is more involved, but still the concept is the same, is the twinkling of stars. This is attributed to the turbulent air whose changing conditions refract the light. So there might be differences in pressure, in temperature, or humidity in the air. And so what happens with starlight is it gets deflected and doesn't reach us. And when it doesn't reach us, we see that the star gets dimmer. So we see this twinkling. Starlight is easy to deflect. It is a very thin ray, since it's coming from very far away. But planetary light is more difficult. It is an extended disk. So if some of the planetary light gets deflected due to the turbulent air in the atmosphere, there is still much light left, and so we do not observe planets to be twinkling in general. Another phenomenon is dispersion. Newton, he passed a ray of light through a glass with a triangular base. This is called a prism. And he found that the white sunlight splits into parts. We say that it disperses. It splits into separate colors. So white light is composed of a spectrum, or different colors. And this happens because different colors refract differently. They get deflected by a different amount. Different colors travel at different speeds in glass, and this is what we're seeing. Now Herschel, the astronomer Herschel, would later put a thermometer beyond this red light, and he would find that the thermometer got warmer. So he discovered another kind of invisible light, infrared radiation. A natural example of dispersion is the rainbow. What happens here is that sunlight enters the raindrop, and the water being like glass, the sunlight disperses or splits into different colors in the water. These different rays, separate rays that have different angles, get reflected on the raindrop edge, and they then get deflected again and exit at different angles. So an observer that is observing this phenomenon will see that the different colors are in separate bands, where the angle that red light makes with the white sunlight, the incoming white sunlight, is different from the angle that the violet or the purple light makes with the incoming sunlight. So the observer sees a band of colors. So this happens when there are raindrops in the sky, as we're familiar with. A more interesting, or also, and it's not more interesting, it's also a very interesting effect. We know that the atmosphere does not glow on its own. It really borrows its light. Its light is the sun's light. But we know also that the sun's light is not blue. It is a spectrum of colors. It is white. What happens here is that the molecules in the atmosphere are better, they're small, and they're better at scattering blue light. In order for us to see the light, it needs to have been sent our way or scattered. So the white light from the sun encounters the molecules, and they prefer to pass on blue light. And so we see blue light. We see blue light preferentially. This also explains the sun at sunset, the red sun at sunset. On its long way through the atmosphere to us, the white light from the sun is filtered. The blue light is scattered, leaving us only the redder light, giving us a red sun at sunset. A property of light is that it is a wave. Waves have an amplitude, a strength, a height or magnitude, a wavelength, the distance from one crest to the next, or one trough to the next, it is all the same, and a frequency, and this is the number of cycles per unit of time, the number of cycles per second that it performs. If it has the same speed, then a low frequency means long wavelength, and a high frequency means a short wavelength. The hallmark of waves is that they can reinforce or cancel each other. So we would have to see that it happens with light as well, just as it happens with water waves. This is called interference. The reinforcement is constructive and the cancellation is destructive. Light was shown to be a wave in the double slit experiment. This is not the quantum mechanical double slit experiment, but just the double slit experiment, an earlier one. here light from a source is only allowed to pass through two narrow slits. And the light on the wall is seen to be a pattern of bright and dark areas, demonstrating interference between the two waves that came from the two different slits. And so one sees an interference pattern on the wall, demonstrating that light is a wave. But if it is a wave, what is it a wave of? Just like we don't have waves in water. So we have waves of water, really, where water is the medium. And this would take some development in electricity and magnetism. So electricity and magnetism were treated as two separate phenomena before Ørsted, the Danish physicist Ørsted. So first, magnetism. Magnetism, we have the magnets, which are objects with a north and a south pole. And two magnets, the north pole and the north pole of two magnets would repel each other, and the north pole and south pole of the other magnet, north pole of one and south pole of the other, would attract each other. And it was used to find the magnetic north of Earth, because there is the Earth sets up a magnetic field, a very large magnet. So the south of the magnetized needle would be attracted to north of Earth's magnetic field. And electricity is related to electric charges. Positive charges, these particles, positive charges repel each other. Positive charges attract negative charges. And currents are really flows of electric charge. Ørsted discovered that current running in a wire sets up a magnetic field around it. So a current, electricity, would set up a magnetic field, something that was otherwise disparate or was thought not to be related. The two phenomena were thought not to be related. And so if one puts a compass near the wire, it will respond, the needle will respond to the magnetic field, and so it will align itself with the arrows. There are electric fields around electric charges. Yeah, an electric charge sets up an electric field. They point outwards from a positive charge. And there are magnetic fields around currents. Both weaken with distance. So as we go away from the electric charge, or as we go away from the wire, the magnetic field gets weaker. Faraday discovered another connection, really the converse. Recall, Ørsted discovered that a current running in a wire sets up a magnetic field. Faraday discovered that a changing magnetic field induces a current in a wire. And so how does one change a magnetic field? One simply, since magnetic fields weaken with distance, one removes the magnet and puts it back in again. And so what happens is that the magnetic field changes near the wire and a current is induced. These observations and others are summarized in Maxwell's equations. Maxwell, he also added a necessary term in order to make it all fit. With experiment, he added a term where a changing electric field contributes to the magnetic field. So we had Faraday, where a changing magnetic field induces a current. And now Maxwell introduces a term where a changing electric field contributes to the magnetic field. So we get to an unexpected realization. Maxwell's equations, they describe the behavior of electric and magnetic fields. These equations predict the existence of electromagnetic waves. Surprisingly, these travel with exactly the speed of light. So light is identified with the electromagnetic wave. And here is the structure. So we have a detached or disembodied wave that can travel in vacuum. The electric and magnetic fields are really bound together. They are synchronized. The electric field and the magnetic field oscillate perpendicular to each other. So one sees an oscillation here of the electric field and an oscillation here perpendicular of the magnetic field, perpendicular to the electric field. And both are perpendicular to the direction of travel, which is this way in this case. And the waves have, again, they have a wavelength, and when one knows the speed, one can also get the frequency of the wave. So different colors are different wavelengths. These, I believe, are nanometers. So we see that red has a larger wavelength, here 780 nanometers, and purple or violet has 400 nanometers, so a shorter wavelength or a larger frequency. And we see that visible light is only part of the electromagnetic spectrum. There are many other things that we cannot see, and all travel with the speed of light. They differ only in the frequency. So radio waves have a very low frequency, and visible light has a very high frequency, and gamma rays have a very, very high frequency. So the visible light is really between the ultraviolet light, the high frequency, and the infrared light, the lower frequency that Herschel he discovered. And this opens up many other kinds of astronomy: radio astronomy, infrared astronomy, X-ray astronomy, and so on. So now we come to some questions. The laws, they predict a wave that travels with a certain speed. In general, the speed we measure depends on the frame of reference. We will measure objects to have different speeds when we are ourselves moving. So if we see that the laws, they give us a specific or certain speed, then we can ask, with respect to whom is it traveling with this particular predicted speed? Is it the same speed at any frame? And what are the results of assuming that? This is what I would like to cover next time. And give an introduction to the theory of relativity. I really believe that it can be explained in an understandable way. And I hope that we will go beyond stars and beyond galaxies and consider the current picture of the evolution of the universe as a whole in next lecture. Also, the early and the late universe. Tonight, the sky above Cambridge is a little uneventful. One may catch Venus on the sky towards west, northwest. So we have north, west here, west, northwest. Here's Venus. If you have not seen it already, it is in Taurus at the moment. Recall that Taurus is near Orion and Gemini. And the sky before sunrise above Cambridge. This is 4:25. I'm sorry, it should have said 4:20. It should have said Monday, 4:25 a.m. We have the moon in Sagittarius towards south. It's low in the sky. Recall that Sagittarius is the teapot, very distinctive, not at the moment because the moon is almost full. The moon is a gibbous waning moon, but almost full, and so it will overpower the stars in that direction. Saturn and Jupiter are between Capricorn and Sagittarius, so they are also near the moon and 10 degrees above the horizon. Mars is in Aquarius, that irregular constellation. It is still lower in the sky, so it may be difficult to see in urban environments, or if there is something blocking the horizon. One may have to wait a couple of days for the moon to disappear from this region in order to see the planets. Recall that the moon travels about 13 degrees per day with respect to the stars, so by Saturday it should have disappeared from this region and left Saturn and Jupiter and Mars left them on their own. So this is the end of lecture 3. Thank you for watching, and please send questions and comments to my email address, amel@nbi.dk. And if you like this lecture, please, or any other lecture provided by CMC, please consider donating to help CMC continue its service to the Muslim community. Thank you very much. Assalamu alaikum. Good night.